Okay, so hello everyone, and welcome to another episode of the Data Science Decoded podcast. Today I am with Nir, Mike, and we have a new adding to our podcast. So, Liron, tell you a little bit about yourself.
Hi, I'm Liron. I have a PhD in AI from Tel Aviv. Ex-Microsoft built and led the domain, built and led the AI in two companies, BioCatch and R1, and I'm very happy to be here. Thanks for having me.
Yeah, we're happy that you joined. It's going to be fun. And how are you, Mike and Nir? Long time?
It has been really long time. I think the last episode we recorded it happened more than 1 month ago. It was quite a tough period. We have some war in the middle, and I'm pretty sure that Daniel got stuck in the United States
Exactly.
for more than 2 weeks. But we are back, and welcome, Liron.
Thank you.
Nir?
Doing good. Can't complain. I was in the United States because I'm living here. So I didn't get bombarded by missiles like you guys. But it's very good to see that this is all behind us, at least for now, and that we can go back to business as usual and record our episodes.
Yeah, that is the reason. Been a long time, and one of the reason Liron joined. We said, okay, took us time to schedule it. So maybe if we're like 4 people, and each time 3 will be available, we'll be able to record more often. And I'll add that I won't go into everything that happened. I would just say that if more people would do math, I think we'll be in a better place instead of doing other things. So with that, we're gonna segue to our paper of this week. And the title is Correlation and Causation by Sewall Wright. And the paper is from 1921. So 104 years ago, and few words about Wright. So he's American and he's a geneticist. So he worked a lot about evolution, focused on evolutionary theory. And this paper was seminal because he introduces here the concept of path analysis. So it's like a precursor to causal inference that some of us hopefully are doing as data scientists. So to infer causal relationships in data. And he worked a lot with Fisher. So again, Fisher comes back in many places, various papers we covered, and also here a little bit. And because Fisher worked also on genetic data. And the funny story, at least according to Wikipedia, is that his parents are like cousins.
First cousins, yes.
So one of the things he worked around is in breeding.
Yes.
So that's a little bit funny.
Yes.
You know, it is Daniel. I guess it's quite remarkable because we know what can be consequences of such marriages, and we see it a lot nowadays in many places. But I'm really happy that such marriage brought us such a talented man like Sewall Wright.
Yeah.
And to
Yes,
add to
Neil.
that, he has 2 siblings which are also very well known in their fields, PhDs, scientists. So it was a good marriage.
Fruitful. It was a fruitful marriage.
And a few more words about like the history before we dive into the paper. So prior to Wright, there was Pearson that he references that had a Pearson coefficient, how to infer some, let's call it correlations in data, specifically linear ones. Then Wright came up with this paper that we're going to go over. Then around this paper was started to be cited again. So like the paper disappeared in the 30s and 40s. Nobody really paid attention because Pearson said you cannot really infer causal relationships and they're not really interesting or whatever. He had his own reasons and he was really influential. So also Fisher joined him saying similar things. So until like the 60s, even nobody paid attention. And slowly in econometrics, they started using it, and then in more like math in the 80s with Judah Perl, revived a lot of the ideas and introduced the causal DAGs, directed acyclic graph, that's based upon this. So this is some kind of a history, so our listeners have context. And cool, now we can go into the paper.
Daniel, you the Pearl also
Yes.
published a some sort of a book for everyone, right? About this, if I'm not mistaken. Yes, the
Here
book
you
of
can
what?
see it.
Yeah.
It's on the shelf.
Yeah.
I would say I read it when it came out, and it prompted me to actually work in causal inference. So I had one job where I did causal inference, and I published a paper on this topic. So I like it a lot. And that's why it's super, in my opinion, influential paper.
Before we dive in, let's just understand the context a little bit. And I don't know the answer. I'm genuinely asking. The concept of RCTs, randomized controlled trials, was it known at this point?
Great question. I don't know if exactly by that name, but I think they had some idea of experimentation, because he writes in the paper that you want to keep all the variables constant and change only one if you want to infer causality. So I think they had some kind of a notion of experiment.
Well, he's referring to also stricter forms of restricting the variable, so restricting it to a singular value, which is not necessarily what you would do for an RCT. And the other piece of question, and Daniel, you would know at least until a few years ago, we still cannot infer the causal graphs, right? We can assume them and then check the relationships.
Yes. You have to make assumptions. There are a lot of assumptions in causal inference. There is the topic of causal discovery.
Yes.
Which is like unsupervised way to build some kind of causal relationships from just data. But of course, also there's a lot of assumptions there. But we'll get into that.
By the way, folks, I just asked the consulted Gemini 2.5, and it states that the first modern randomized controlled trial RCT was conducted in 1946, 25 years before this, by British.
No, after. If it's 1946.
After. Yes, by British statistician Sir Austin Bradford Hill for the UK's Medical Research Council.
Cool. So that
according to Gemini,
Okay, so let's dive in the paper. Sorry, Liron.
I'm also looking at Wikipedia, and it's also saying an early essay advocating for blinding researchers came in the later half of the 19th century.
No, but that's double blind if you're a blind researcher, not just
it's also the 19th century, it's the 1800s. Yeah, but I didn't reach RCTs here yet. Yeah, the first published RCT, 48.
Okay. Gemini stated that it is 46, you can't trust your LLMs.
Well, you used to not be able to trust Wikipedia, right? It's not a serious encyclopedia.
You can average them, so it is 47.
What happens if you take the median?
More or less the same, these numbers are really close.
Yeah, for our purposes, that's good enough. So, okay, the plan for our listeners, there's a lot of... It's a long paper first, and there's a lot of various equations, not complicated ones, but we won't be able to cover all of them in a reasonable amount of time. So the idea is to go over more the higher level of the paper, each important chapter, what it's trying to convey, and the important topics. So I'm going to read the introduction because it's short and to the point. So it says the ideal method of science is the study of the direct influence of one condition on another in experiments in which all other possible causes of variation are eliminated. So at least his definition of science, Liron, sounds like an RCT. Unfortunately, causes of variation often seems to be beyond control. So not always you can experiment. In the biological sciences, especially, one often has to deal with a group of characteristics or conditions which are correlated because of complex or of interacting uncontrollable and often obscure causes. The degree of correlation between two variables can be calculated by well-known methods, but when it is found, it gives merely the resultant of all connecting paths of influence. So he is already like talking about paths. The present paper is an attempt to present a method of measuring the direct influence along each separate path in such a system, and thus of finding the degree to which variation of a given effect is determined by each particular cause. The method depends on the combination of knowledge of the degrees of correlation among the variables in a system, with such knowledge as may be possessed of the causal relations. In cases in which the causal relations are uncertain, the method can be used to find the logical consequences of any particular hypothesis in regard to them. Cool. What are your thoughts on the introduction?
Clear and
Sounds
concise.
good, self-contained.
It sets up the kind of language we'll see throughout the paper. Like, it has some sentences that are very accurate mathematically, but so dense. You need some time to unpack this in your mind.
Yeah, so he was mostly doing genetics, but he had background in math. So first chapter is correlation. And here I won't dive into the math, but he talks about coefficient of correlation, and he cites Galtons, which is the way that we can look to this as the expectation between two variables, in a sense. The normalized one, so it's like the Pearson coefficient, we call it today, right?
I think it's different here from what we call Pearson today. Pearson today is more similar to the first one.
That's right. I'm talking about the first one, which he calls Galton. Yeah, we call it Pearson. And then he has Pearson correlation, which is more like conditional.
Yes.
Some kind of conditional expectation, as far as I can understand.
It's a conditional standard deviation of x given y.
It's kind of a directional one, and the interesting is the first definition is if you multiply both directions of the second definition. So if you take correlation, if you take the correlation from x to y and then from y to x and multiply them, you get the first definition.
Sounds reasonable. I didn't check it, but I rely on you that it is. It looks correct and it sounds correct. So let's assume that it's correct.
I will say I'm 99% sure.
Okay.
Good enough.
Let's continue.
The LLM's age.
He says Liron might be hallucinating. Anyways, the use of a coefficient of correlation R, so again, what we call Pearson correlation, assumes there's a linear relation between the two variables x and y. So that he says that a given change in one variable always involves a certain constant change in the corresponding average value of the other.
Yeah.
By the way, this sentence is not very precise. This correlation measures linear relationship between variables. These variables can be related on many nonlinear ways, but this coefficient doesn't measure it.
No, exactly.
That's true.
So you could say that the correlation coefficient is the Koopman linearization of the relationship between the variables.
Okay.
The what, Koopman?
I have no idea what you mean by that. I'm not a mathematician.
You know Taylor linearization, right? Where you say, okay, I approximate linearly, but Taylor linearization is on an epsilon environment. So if you look at the bigger environment, you have to say, okay, if I look at the distribution of one of the variables, what's the best linear approximation over this distribution? And this is called Koopman linearization.
It is not so known, but you know.
It's the same Koopman from dynamic systems, Liron?
Probably, I didn't check.
Okay. Yeah, it's also a linearization technique for dynamic systems.
Yes, it's the same linearization technique. It's used for dynamic systems.
With the Koopman operator, yes?
I do not recall the name, but it makes sense.
Cool. So let's continue. He just defines here. He gives like the background to what was known at the time to measure relationship, which is the correlation, which is linear. And there's the correlation ratio. Again, as we said, it's the expectation of the standard deviation. At the end, it measures also nonlinear relationship, as far as I can tell. and it's between 0 and 1.
It says something very interesting.
Where?
I don't remember if it's this paragraph or somewhere around here, that the correlation is at its smallest value if the relationship is linear, but otherwise it's more than that, which was weird. I think he means the second moment if it's 0.
Oh, I have no idea what you're talking about.
Okay.
But
Well,
maybe.
let's see if we get to this sentence.
What he calls the correlation coefficient is the second moment's square rooted. Is the standard is the population standard deviation given something else is fixed. That's how I understand it. So it's a condition.
Yes, you're right. It's not a second moment. I meant a quadratic relationship.
Yeah.
But
yeah.
You're right. It's not a
We
second.
won't go into it due to time. I'll just go over what he says here. Now we should like generalize it. Now, if you have more than 2 variables, so you get like a matrix and you calculate the determinant of the matrix, right?
This is a correlation matrix, I think.
Yeah. So again, basic things. We won't go into them. Maybe if you tell me there's something relevant here.
I did not understand it as a correlation matrix because it has, but it has by definition identity on the main diagonal, which is not true for a correlation matrix.
He assumes that the main diagonal, there is a unity variance here. I think that's what I understood. And the off-diagonal elements it's a symmetric matrix with the off-diagonal elements being the correlation coefficients. That's how I understood it. But maybe I'm wrong.
What do you see as delta XX here? Because, I mean, you cannot divide by a matrix.
That's the part of determinant. There's a name to that. I forgot.
Yeah, the self-determinant.
Yeah, I think that's what it means.
I think he mentions it in the next paragraph of the first paragraph of the next page. Is minor.
Oh, minor, he called it. Okay, cool. Anyways,
but you see,
again...
Okay, I think it's not important to understand the paper.
Yeah. Just to our listeners, it goes over like the definitions of if you have data, you have variables, and how you calculate various correlations between them. And there's a guy named Israelis. So
anyway, I think most of the section is talking about of how we can measure change of one variable given some unit change or given some small change of the second variable or other variables. And all these formulas are quite complicated, and I think most of them are not in a big use for now, at least. But maybe I'm wrong here. I'm not doing such math for many years.
Okay, so this chapter is also important. It's titled causation, and it says, in all the preceding results, no account is taken of the nature of the relationship between the variables, and the calculation thus neglect a very important part of the knowledge which we often possess. There are usually a priori or experimental grounds for believing that certain factors are direct causes of variation in others, or that other pairs are related as effects of a common cause. In many cases, again, there is an obvious mathematical relationship between variables, as between a sum and its components, or between a product and its factors. A correlation between the length and the volume of a body is an example of this kind. Just because it involves no assumptions in regard to the nature of the relationship, the coefficient of correlation may be looked upon as a fact pertaining to the description of a particular population, only to questioned on the grounds of inaccuracy in computation. But it would often be desirable to use a method of analysis by which the knowledge that we have in regard to causal relations may be combined with the knowledge of the degree of relationship furnished by the coefficient of correlation. So he says, I am a researcher in field X. I have some a priori knowledge about relationships of what's going on. I want to use math in a way that complements my knowledge. If I'm going to use correlations as they use, okay, I get numbers, how I combine it with some things I already know. So I think that's like his problem that he's trying to solve with this paper.
I understand it that way as well. So like he's actually stating like so far, I could either do the statistical analysis and learn from the data, or I could use my own knowledge of the relationship. But I want to do both of them together because I know the direction of the relationship, but I don't know the strengths of the relationship. So let's find a way to put the two together.
By the way, I'm using similar statements today when I'm talking data scientists who are developing machine learning models. I'm telling them, but basically I'm telling them that you can't build a good model if you don't have any domain expertise, or at least you are not accompanied by some domain experts. So it's just more or less the same. You can compute correlation, you can build your model, but if you don't really understand the relationship between variables, it can be meaningless in many cases.
Mm-hmm.
At least how it is the way I see it.
Let's give a classic example, right? So if you try to do business analysis and you look at marketing, and you can say, well, if you spend more money on marketing, marketing actually becomes less efficient. And you can find that correlation in the data. And say, hey,
Yeah.
I'm a great data scientist, I analyzed it. And you go to the business people and you tell them about that. They're telling you, no, that's ridiculous. It cannot be possible that we spend more money to sell less. We're not that stupid. And, indeed, they are not that stupid. It's not what's happening. So what's actually happening is when the market gets tough, companies spend more on advertising, but they also get the adverse effect of the market being tough.
Yeah.
So you actually see where there is actually a causal positive relationship between spending and leads or spending and revenue, you actually see a negative correlation in the data if you don't know the kind of causal graph you should use here.
So you had in your story, you had a co-founder, confounder.
Confounder, not
Yeah,
co-founder.
I'm a co-founder of a startup. True.
Yes.
You don't want to be confounder, right? You want to stay
Daniel, you're a
co-founder.
confounder now.
I'm gonna change on LinkedIn. Confounder and CTO.
Don't tell your co-founder he's a negative confounder. That's not gonna work.
Yeah, thanks.
Thank you.
The listeners and the viewers can see here, Wright gives like a more complicated causal graph of a problem of like raising guinea pigs in a lab and measuring various features of variables. And I think like the outcome is the weight at 33 days, and there's a lot of like variables that can affect that. And he draw like arrows, what affects what. And he talks about like this problem because he has some a priori knowledge of what affects what variable. And he wants to have a model that can incorporate that.
I think it's a great example of a few things. He really saw this out. First, it's a great example of how domain expertise would really help because that's his domain, genetics.
Yeah.
And the other thing is he wasn't going for like the simplest example to understand. He actually gave a complicated example with multiple factors affecting the same things, and he goes in the text to a bunch of examples where those things would have contradicting effects and how that all plays together. So if you really want to follow a complex case, this is a great example.
Yeah, and we won't go over it, but you can see it here. He talks about it. And you can calculate various coefficients and do some ways to try to find the exact effects. But again, we won't go over his example. We're going to continue to definitions. So now he's trying to provide a framework to solve those kind of problems. Here he talks about, I think it's first linear relationships. Let's see if I'm right.
I think you should read at least some sentences from this paragraph. It looks like important, I think. What do you think, guys?
Let me see. Some parts are important, I agree.
Is important, I think.
Yeah, some part.
Where do you recommend me to start?
You can start here. The expression sigma x dot a. Can you see it?
Okay, yes. Will be used for the standard deviation of x. And x is the dependent variable, and a is the independent variable, or cause. Okay, so x is the outcome.
Yeah, effect.
And a is the cause. And he says sigma xa will be used for the standard deviation of x, which is found under the foregoing conditions, and may be read as the standard deviation of x due to a, in a system in which variation of x is completely determined by a, b, and c. We have a sigma x dot a equals sigma a. Well, I'm not sure what's happening here. I think he multiplies at the end. He multiplies the two
Read the next sentence.
standard deviation. It represents the constant factor B and C, and also the variation of A itself by sigma A.
Maybe it just defines the dependence of
What?
X by B and C just as factoring,
I think that what's important here is that he said that the path coefficient Pxa is the standard deviation of x given A divided by the whole standard deviation of x. Yeah. And I like this definition.
That's kind of similar to how we use Pearson today.
Yes, yes.
It says the path coefficient for the path from A to X will be defined as the ratio of the standard deviation of X due to A to the total standard deviation. Yeah, it's normalized. And I think he says when you assume linear relationships, each connection between the variables in your path diagram is the Pearson correlation.
So this is what we would call explained variance, or in this case, explained standard deviation.
Yeah. And then let's see, and there's another coefficient which will be convenient to use, the coefficient of determination of X by A. dx A measures the fraction of complete determination for which factor A is directly responsible in the given system of factors. This definition implies that the sum of such coefficients must equal unity if all causes are accounted for.
Yeah.
So
that's the variance.
What do you say?
I think that's the variance ratio instead of the standard deviation ratio. That's how I understand it.
Yeah, it's very confusing that he's not giving a mathematical definition here together with the verbal definition, because he does give that a bit later on, or at least some examples.
Yeah.
I think for me, maybe I'm wrong, but for me, he's talking about as extent of dependence of X by variable A. And if X is depends or is caused by causes 1, A2, A3, the sum of these D coefficients for all these variables should be 1. So it is my understanding of this.
Yeah, the question is, what is it more than a sum of 1? Because I can take a bunch of coefficients that are non-negative and sum up to 1, and you can apply, say, some power to them and renormalize, and you get something which also equals to 1, but you actually change the relationship.
Yes, it is unclear.
Down here is actually defining it. It's dxa equals sigma squared A over sigma squared X, which is this path coefficient squared. So it makes sense that it normalizes everything. The sum will be 1 because it normalizes by the standard deviation by the variance of X.
Yeah. So this chapter is system of independent causes. So that's easy if they're independent. So if there are two causes A and B, the standard deviation of the sum is the standard deviation of each cause, but also you have the multiplication because they might be independent. They might be dependent. So you have two variables might be affecting each other. So you have the variance of the sum is each variance plus the multiplication. But then he says if they're independent, so there's no correlation between them, so it's just the the standard deviation of each one squared. And you can combine them, which again, we know this today as well. This is like basic stuff. I want to see what else is important.
By the way, they can also be dependent, but zero correlation.
That's right.
Yeah, but this also works the same way.
Yeah, I think we talked about it in one of our episodes.
Yeah.
But they are allowing correlation here. Right? It does appear in the beginning. So I think the sense of independence he's talking about is that none of them is a cause for any of the others.
Exactly.
Yes.
Exactly. Chain of causes. Chains of causes now. So now if you have a few causes, so it says, if we know the extent to which a variable X is determined by a certain cause N, which is independent of other causes, and combines with them additively, and X on X in a linear manner, so he assumes here additivity and linearity, then you can say that X is combination of M plus N, and then it's easier to calculate the standard deviation of each one.
By the way, guys, I think we forgot to emphasize that here we have been talking about additive cases, and all these dependencies between causes and dependent variables are linear, and all we said relate to this case. And now we are going to address non-negative dependencies.
Non-additive, you mean?
Non-additive, so no, not negative, non-additive. Yeah.
So here it says an example: if x is affected by a and b and a multiplication of a and b, okay? And then, I don't know, your BMI, for example, right? It's some kind of derivative of your height and your weight. And somehow they both affecting, and just example came up to my head, right? Head. So then
a very simple example is if you take the height and width of a rectangle, that defines the area. Right? Very straightforward.
Mm-hmm. Yep.
Yeah, that's also multiplication. But then he says, okay, now it's, if you want to calculate the standard deviation, now, well, it's not so straightforward as in an additive one, and he has here the formula. I have no intuition why it is like that, but I think he probably knows what he's talking about. I don't know, you're familiar with this? Makes sense?
It's hard to say. I think it is just a computation of dependency extent of x by a and b in the case of multiplication. I guess these formulas are correct. But by the way, what is important, what I didn't see here, we're talking about relationships, but the data we have is not a clean data. All the data we have, there is some noise which is added to the data. So all these formulas, we need to take it not with a grain of salt, but with the abuse of notation, that your measurements have also noise inside. And the word noise doesn't appear in this paper. We're talking about variances and stuff, but we also have some noise, okay, in the measurements of x, y, n, and b.
Yeah, everything.
It doesn't appear here. So you need
but
to be.
Look, it's you're right, but only like the same year, Fisher had this paper about estimation and some kind of probability definitions of concepts when you have noise, like maximum likelihood and stuff, right? So we didn't have it.
I don't see that as a problem, by the way, Mike. I think it's inferred from the paper, because when you talk about variances and correlations, it's always about noise. Otherwise, it's deterministic and you don't have any variance. So I don't know.
If you had PhD in math or in electric engineering, it is clear for you, but I'm not sure it is clear for everyone. This is the reason I've made this clarification. Okay.
But I think you're touching even bigger point, that all the assumptions here are assuming linearity, and to some extent it assumes everything is jointly Gaussian, because that's how you can calculate correlation matrices and derive a lot of meaning from them. But if your distributions here, for example, were heavy tail, many of these calculations wouldn't actually work. So there is a limit to that, but it's so early in the development of math that this is a huge step forward, it would seem.
What do you mean by that, Liron? You think that why jointly Gaussian? Why the calculation won't work? Can you elaborate on that?
Yeah, so let's take a very concrete point, which I know. So let's assume that variables are, say, have heavy tail distribution like Cauchy, right?
Okay.
And if you take a Cauchy distribution, the moments are not finite, or they don't exist.
Right.
But if you infer their statistics from the measurements are always final. So you will get some estimated statistics. And if you don't account for this option, you will get something that is practically meaningless.
Yeah.
So that's kind of an extreme case I have in mind. Now, in this case, I'm not sure if it wouldn't work at all, but you can think about, for example, Laplace distributions, right? Or even exponential distributions. So if you just calculate correlation matrices, you would get some results, and it would be true if you're looking at the exact same distribution of the population. But it will not generalize to a different population or even to a different experiment if you don't have enough data.
Yes, if you don't have enough data, you're right, absolutely right. Yeah, it's but still, what other, if you don't have enough data, what other in statistical tools, what other tools except for the sample correlation matrix or coefficient or sample variance or sample standard deviation you can use? Maybe the sample median, maybe the sample absolute value of differences.
So
I don't know.
everything in robust statistics will be relevant here, of course.
Yeah.
But I'm taking this back to Mike's point about noise. So if the noise is not Gaussian, what you would get is this will be very vulnerable to errors in measurement. But if you add instead where you have Laplace distributions, you would add lasso regularization instead of ridge regularization, you would get something that works much better. Of course, you never get a real Laplace distribution, right? And you can get something which is kind of similar, but it would still work well. And the more meaningful the heavy tail, the more you need to have an L1 term in your, what's that called? Elastic net regularization.
Difference of absolute values, different absolute difference. I agree 100%. The L1 term is crucial for these kind of heavy tailed.
Yes, and you don't actually need L1 per se. There's a term that I forgot for the loss, which is L1 where it's far from the origin. I'm pointing the wrong way. L1 where it's far from the origin, then it becomes like L2 when it's close to the origin. I think it starts
Huber
with an
loss.
H.
It is Huber loss.
Huber, yeah.
Huber, Huber, I guess.
Yes.
Okay, let's continue. So we will be able to cover the paper. So now he says, okay, what happens when there's effects of common causes? So to our listeners that cannot see the paper, there's two outcomes, variables that we're interested in, X and Y, and they both affected by B, C, and D variables. And also there's A that affects X and E that affects Y. And then he formalizes a way that we can calculate each path. And he shows also here how it all sums up to one. So that's the
I just got to admit our listeners that here the formulas got really cumbersome, so they're not gonna explain these formulas. You know, each formula here is almost one line.
Yeah, and now he talks about correlated causes. So we talked about it. So if you have an outcome X, so it's a standard deviation of each cause, but also the multiplication of them because they can work in tandem also and reinforce each other, for example. So he gives an example. Again, the whole idea in the paper is here. You draw your variables, you draw the connections that you know a priori between them. And it shows that the connection between like the nodes, the path itself, it's the correlation that you can calculate, right? So he says, okay, we can calculate correlations. So we can now draw all the paths and calculate how much each one affect others when I keep, how each one affect the one I want to calculate when I keep all the others constant. So that's part of what he describes here.
I think at least what I understood from the message here is that zero correlation that does not mean there is no common causes.
Yeah, that's true.
Right?
Yeah. If the variables are dependent, so yeah, you can have a case when like two variables like negating each other.
Yeah, exactly.
And you get a zero correlation, but in fact there is causal effects.
Like in bad startups, mutually canceling co-founder.
Yeah, that happens with you and my co-founder. No, just kidding. Okay. I don't know if he's going to listen to this episode. Okay, so and now we're going to summarize the paper. He gets to the general formula. So now he assumes that there is also like the causes could be dependent on each other. So you have all these multiplication terms, and he gives a few, and then he gives some examples of real data of guinea pigs and calculates a lot of correlations. And he draws like, think about variables, and he draws the arrows, the path, and calculates the correlation between them.
Yeah.
Let's see. Yeah, he does it a lot. I want to see if there's something interesting towards the end on the paper.
It is a
Some
really
kind
tough
of
paper. I think it is one of the toughest papers we covered. We had the 30 episodes. I think it is third place maybe.
no,
in
it's a
this
long paper. It's like, I don't know,
long, but it
30.
is not very trivial as well.
Okay, cool. So there is the end when he talks about other application. So not just like genetics and inbreeding. As I said prior, it was used a lot in econometrics, and because they started to gather a lot of data about people and then try to understand who's going to get wealthy, etc. Yeah, so guys, what are your thoughts? Have you ever used the causal tools in your work? I'm curious.
I've never used it, and
Me neither.
I admit that I never studied it as well. And I have a question to you, Daniel, as the biggest expert among us in causal theory. How
Causal.
these papers, how has this paper shaped the modern causality theory of Judah Pearl?
Yeah,
I'm
there's
explaining. I'm
Pearl,
explaining.
and there's another framework of counterfactuals by Rubin. I would just say that to our listeners, so you might be data scientists and you never use that, because I'll tell you why. If you have ability to do experiments, right, you don't need causal inference. So causal inference is like used when you have data, usually historical data. You cannot tweak anything, you got it. And now you're trying to answer some questions about it. Right? You're trying to infer something. And then if you use various tools, let's say neural network, whatever, trying to understand something, you lose all the causal relationship that the data originally had. And then that's where causal inference comes, like in the example that he talks in the paper. Okay, I know, let's say I'm in domain of marketing, as Liron said, I know some things about causality, right? So first we're going to call the person, and then he's going to decide if he's going to buy, right? So if I have the data, he cannot buy, but then we call him, right? So there's some causality in the physical world. So if I know it, I can build that, like similar to what he did with paths and variables. We call it DAG, directed at cyclic graph. And we can use similar tools to answer questions about historical data. But if you work in a place you can do experiments, so probably don't need that. Yeah, sorry, Leon.
Yeah, no worries. So those would be dogs directed as cyclic weighted graphs when you weight them by the correlation coefficients, which is actually very interesting because most of the graph algorithms, I'm not sure they generalize well to weighted graphs. So if you're going to use graph algorithms here, it will be more complicated.
Yeah.
But what the point I wanted to make about experiments is if you're able to control the experiment for the variable you want to measure and randomize everything else, then you have a good setup for an experiment. But if you're just getting data from the wild and want to kind of preliminary check your hypothesis that the causal relationship doesn't break, so there is kind of a middle point there that I'm aware of, that you want to take the data, but there's a way to renormalize it so the different groups have equal weights.
Yeah, it's called positivity in causal inference. Anyways, I understand where you're going, yeah.
So I just wanted our listeners to be aware of this middle point where if you cannot do a randomized control trial and you don't know the exact relationships, you can work with this method on your experiments to get a better initial inference of the relationship.
Yeah, for sure. And now, Ed, that's why it was affected a lot by Bayesian inference, because here we have like some kind of a priori model with some confidence about the world, and I have the data, and I want to combine them, right? So that's exactly a Bayesian inference. To what Liron said, yeah, like if I'm starting a experiment and it's running, but I get preliminary data, it's still better than no data at all. So that's the Bayesian way, right? They're not saying, okay, I'm going to wait until I reach a power of something and p-value or whatever. They just, whatever data I have, I work with that. So a causal inference is using a lot of Bayesian methods, a lot, like often, and also Monte Carlo happens there a lot, as a paper we covered. So yeah, in my opinion, I'll just add that it's interesting field because you cannot just do, I'm going to do a neural network or a random forest and I'm going to hyper parameterize and find the best whatever and cross validate all the methods we do. We still need the domain expert. We still need to think causally and trying to understand what actually happens in the world. And I liked it a lot. It felt more fun for me. Yeah, so that's my point. And yeah, I guess that's it. Probably we're going to cover some Judah Perl papers, but they're from like 80s, 90s, so we'll get to that later. And yeah, so thank you, Liron. How was your first paper, sorry.
Well, I hope it's not the average level of difficulty. Mike was very relaxing in that regard.
It is not average. Yeah, it is about average level of difficulty. I guess at least for me, this paper was tough on me because I don't have almost any preliminary knowledge about causal inference. So I guess our next papers will tend to be simpler, but I can guarantee you that.
Well,
Mike, simpler, he has some kind of Weierstrass distance in a hyper-dimensional space,
Yeah,
like integrals, that's simpler, I have no idea what's going on.
That is simpler, but I mean, for me, the challenge wasn't the background because he didn't have any background in causal inference. He was basically trying to invent it here. For me, it was hard in terms of the notations and how far away are they from what I'm used to. So I have to kind of sit with a notebook and try and write things in his notations to understand where he's going, and that's still confusing. So that's what made it much harder for me to understand.
Cool. So again, hopefully next one will be more abstract or hopefully less abstract. I don't know. Depends on your preferences. But thank you. It was fun and good to be back. And hopefully we'll get on a routine now. And I wish everyone a great week. Also to our listeners, have fun, enjoy life, do math, read math, work out, and see you next week.
Bye, guys.
Bye.